Every once in a while, a discovery reminds us just how close we're getting to answering the question that's haunted us for centuries. Are we alone? This time, that moment came from a small, faint star about 40 light-years away. TRAPPIST-1. The James Webb Space Telescope has just taken a closer look at one of its planets, TRAPPIST-1e, and what it found is both exciting and confusing at the same time. The data doesn't give us a clear yes or no. It gives us two possible realities. One where the planet is nothing more than a bare, airless rock drifting around its star, and another where it's hiding something thin, fragile, and possibly familiar, an atmosphere not unlike our own. Before we jump into the details, understand this. This is the closest we've ever come to studying a truly Earth-like world beyond our solar system. And if Webb's observations are right, then what's happening around that tiny red dwarf star might completely reshape how we think about life outside Earth. The TRAPPIST-1 system doesn't look like much at first glance. It's small, faint, and cold, the kind of star you'd probably ignore if you were scanning the sky for something that looks like our sun. But that's exactly what makes it interesting. TRAPPIST-1 is an ultra-cool red dwarf, the smallest class of star that can still fuse hydrogen and shine for trillions of years. It's about the size of Jupiter, only slightly heavier, yet it manages to host a whole family of Earth-sized planets tightly packed around it. The system sits about 40 light-years away in the constellation Aquarius, close in cosmic terms, far in every other. Astronomers discovered it in 1999, when the star itself was first identified, but its extraordinary seven-planet lineup wasn't revealed until 2017, using a telescope called TRAPPIST. The ground-based TRAPPIST optical robotic telescopes, TRAPPIST South in Chile's Atacama Desert and TRAPPIST North in Morocco's Atlas Mountains, employ a method called transit photometry to detect periodic dips in stellar brightness. The project, led by Belgian astronomer Michael Gillen, was later supported by NASA's Spitzer Space Telescope, which confirmed the details. What shocked everyone was how compact it was. All 7 planets, labeled B, C, D, E, F, G, and H, orbit closer to their star than Mercury does to the Sun. If you could stand on one of them, you'd see the others hanging in the sky, some big enough to spot with the naked eye, like moons. The whole system fits easily inside the orbit of Mercury, yet each planet is roughly the same size as Earth. That's the kind of thing no one expected to find until TRAPPIST-1 came along. Now, out of those 7, TRAPPIST E, F, and G lie within what scientists call the habitable zone. That's the region around a star where temperatures could allow liquid water to exist on the surface, assuming there's an atmosphere to trap some heat. Too close, and the planet becomes scorched. Too far, and it freezes solid. But one of them stands out, TRAPPIST-1e. It sits right in the sweet spot, getting about 2/3 of the energy from its star that Earth receives from the Sun. It's also dense enough to suggest a rocky surface, not a gas envelope like Neptune. That combination, right size, right temperature, solid surface, makes it the most promising of the bunch. Before the James Webb Space Telescope came along, astronomers already had clues about TRAPPIST-1e. They knew its orbit takes just over 6 Earth days, that it likely faces its star with one side always in daylight and the other in endless night. They knew it probably lost some of its early atmosphere to the star's radiation. Red dwarfs are violent when young. They flare up often, throwing out bursts of high-energy particles that can strip a planet bare. But they also calm down over time, and if a planet manages to rebuild a secondary atmosphere after that stormy period, it might settle into something stable. That's the hope for TRAPPIST-1e. When Webb launched, scientists knew this was one of the first places it needed to look. It's close enough for Webb to study, bright enough for its instruments to catch transits, and interesting enough to matter. If TRAPPIST-1e has an atmosphere, Webb's infrared eyes should be able to detect it. That's what makes it such a key test case. It's not just another exoplanet, it's a scale model of Earth's early years. The kind of planet that could show us how common worlds like ours really are. Another reason this system draws so much attention is that it's the perfect natural laboratory. 7 planets, all the same size, orbiting the same small star under slightly different conditions. That means we can compare them directly. If one has an atmosphere and another doesn't, we can start asking why. Is it because of their distance from the star, their composition, or the amount of radiation they've endured? Each one tells part of a story, and TRAPPIST-1 might be the chapter that answers whether these worlds are capable of supporting life as we understand it. That's why this little red dwarf system, barely glowing compared to our Sun, has become one of the most studied places beyond our solar system. It's not because it's beautiful or massive, it's because it's relatable. Every planet is a reminder that Earth might not be unique. And among them, TRAPPIST-1e is the most promising mirror we've found so far. It's the world that makes astronomers stop and wonder what it would be like to look up from its surface and see not just stars, but 6 other Earth-sized worlds drifting through the same sky. When the James Webb Space Telescope turned its attention there, it wasn't just to capture data, it was to test a question humanity has carried for as long as we've been able to look up. If Earth isn't alone in its kind, then what's waiting out there in systems like TRAPPIST-1? When Webb turned toward TRAPPIST-1e, scientists weren't expecting miracles. They just wanted clarity, a clearer signal than any telescope before it could provide. The plan was simple. Watch as the planet passes in front of its star, capture the faint starlight that filters through whatever atmosphere might exist, and break that light down into its chemical fingerprints. This technique, called transmission spectroscopy, works because every molecule absorbs light differently. Oxygen, carbon dioxide, methane, water vapor, they all leave unique imprints in the light. If a planet has an atmosphere, Webb should see those marks. But there's a catch. TRAPPIST-1 orbits a small, restless red dwarf. That kind of star isn't calm like our Sun. It flickers, flares, and constantly changes brightness. Those changes can mimic or hide the signals scientists are looking for. Even so, Webb is powerful enough to separate most of that noise. The team collected data during several transits, each one lasting less than an hour, with the planet crossing in front of its star again and again. Each pass gave Webb another chance to catch the faintest trace of atmospheric gases. What Webb saw was more complicated than expected. The telescope's NIRSPEC instrument recorded variations in the infrared light during each transit. But those variations weren't only coming from the planet, they were tangled with the activity of the star itself. Tiny dark spots on the star's surface, cooler regions known as star spots, distorted the signal. Bright patches did the same. In other words, the star wasn't sitting still, it was interfering. After carefully removing as much stellar interference as possible, the scientists analyzed what remained. The results left them with 2 possible stories. In the first, TRAPPIST-1e has no real atmosphere at all, maybe only a trace of gases clinging to a barren surface. That would mean it's an exposed, airless rock, stripped clean by the radiation of its star long ago. In the second scenario, the planet does have an atmosphere, but it's not thick or hydrogen-rich like Neptune's. Instead, it could be a thin, dense shell of nitrogen, similar to Earth's dominant gas, possibly mixed with trace amounts of carbon dioxide. Either way, one thing is now certain. TRAPPIST-1e does not have a hydrogen-dominated atmosphere. Webb's sensitivity ruled that out entirely. That's a major step because it tells scientists the planet didn't hold on to the thick, primordial gases that many small worlds start with. In other words, it's evolved. It's more like Earth or Venus than a mini Neptune. That's a crucial clue for figuring out which planets might be truly habitable. The most interesting part of all this isn't what Webb confirmed, but what it hinted at. Some of the data patterns, small shifts in the infrared light, could be consistent with a nitrogen atmosphere hiding behind clouds or haze. It's not proof, but it's enough to keep scientists cautious and curious. A planet with even a thin atmosphere around a red dwarf star would challenge current models of how much radiation those stars can dish out before stripping everything away. If that's true for TRAPPIST-1e, it means atmospheres might survive longer than we thought, even under extreme conditions. Still, the team is being careful. They know what it would take for the signal to mislead them. Star spots, flares, even minor temperature differences on the star's surface can trick instruments into thinking they're seeing gases when they're not. So for now, no one is declaring a discovery of life, or even a confirmed atmosphere. The data shows no strong evidence for or against a thin secondary atmosphere, with equal likelihood for either scenario. But what Webb achieved here is remarkable on its own. It measured changes in starlight from a planet the size of Earth, orbiting a faint star 40 light-years away, with precision fine enough to detect molecules thinner than a wisp of air. Before Webb, that kind of data was impossible. The Hubble Space Telescope could spot atmospheres around giant planets, but never around worlds this small or this faint. Webb's infrared eyes changed that. Even if the result isn't a headline-making confirmation of a breathable world, it's a major leap in how far we can push our tools. It's like finally being able to see the outline of something we've only guessed at for years. When scientists looked at Webb's results, they realized they were standing between two very different worlds. Both fit the data, and both tell completely different stories about what kind of planet TRAPPIST-1e really is. In the first picture, TRAPPIST-1e is a silent, lifeless rock. Its star stripped it bare long ago, leaving nothing but a cracked surface and thin traces of gas too faint to form a real atmosphere. Without a thick layer of gases to hold in heat, the planet's surface would swing between extreme temperatures. The side facing the star could bake in constant light, while the far side, locked in permanent darkness, would freeze solid. If that's true, then what Webb saw wasn't the fingerprint of an atmosphere at all. It was the signal of starlight bouncing off a dead, airless world. That idea might sound disappointing, but it's still an answer to a question that's haunted exoplanet science for decades. Can small planets around red dwarfs even keep their air? If this version is real, the answer is no, not for long. The radiation, the stellar winds, and the constant flares simply tear atmospheres away faster than they can recover. But the second picture is harder to dismiss. In this one, TRAPPIST-1e did survive the chaos. Maybe it lost its original hydrogen-heavy atmosphere early on, but built a new one later. A secondary atmosphere formed from volcanic gases, chemical reactions, or impacts. This one would be mostly nitrogen, with traces of carbon dioxide and maybe even water vapor, thin, dense, and probably cloudy. If you stood there, you might see a hazy red sky, dim sunlight, and a faint glow from the nearby planets reflecting light from the same star. The air wouldn't be breathable for us, but it would change everything we thought we knew about these worlds. It would mean that planets around small stars can rebuild what's been lost. In both possibilities, the same data holds the key. It just depends on how you read it. The lack of hydrogen features is the clue that rules out a thick, puffy atmosphere. That's what makes TRAPPIST-1e interesting. It's compact, rocky, and dense. So, even if it has an atmosphere, it's likely similar in scale to Earth's or Venus's. What matters now is how much of it remains. If the nitrogen scenario turns out to be true, the planet could maintain surface pressure high enough to keep water stable. If not, it's too thin for liquid water to survive. Everything would freeze or evaporate away. What Webb showed, without a doubt, is that we're finally working at the right scale. We're not studying gas giants or warm sub-Neptunes anymore. We're looking at a real Earth-sized planet with the precision to detect the difference between a thick atmosphere and none at all. That's a level of detail scientists have been chasing for years. Even with uncertainties, the fact that we can see hints of a nitrogen-based composition is huge. It suggests that terrestrial atmospheres may exist elsewhere, just hard to detect. Another thing worth noting is that both scenarios tell us something valuable about habitability. If TRAPPIST-1e is bare, it teaches us about the limits of life, how far a planet can go before it becomes uninhabitable. If it has an atmosphere, even a thin one, it shows us that habitability might persist under harsher conditions than expected. Red dwarfs make up most of the stars in the galaxy, so knowing whether their planets can hold on to atmospheres changes our entire estimate of how common habitable worlds could be. This is why ambiguity isn't failure in science. Every time a telescope like Webb gives us uncertain data, it's pointing to something deeper. In this case, it's showing how close the line is between a dead world and a living one. Both realities could be true. One means the planet is quiet, frozen, and done. The other means it's still breathing, even if faintly. And right now, no one can say for sure which version we're seeing. But that's the beauty of it. The uncertainty itself is a sign of progress. It means we've reached the edge of what's measurable. The next steps will push that edge a little farther, until we finally know whether TRAPPIST-1e is a silent rock or a world that still carries air. Even though Webb didn't find a clear, unmistakable signature of life or even a full-fledged atmosphere, this discovery changed how scientists think about planets like TRAPPIST-1e. It's not always about what we find, but about what we can now see clearly for the first time. Before Webb, these kinds of observations were guesswork. We could only speculate about whether small rocky planets around red dwarfs could hold on to their air. Now we have real data, imperfect, noisy, but real, showing us how close we are to separating fact from imagination. The reason this is so important is simple. TRAPPIST-1e is the best test we have for understanding what makes a world habitable. If it truly has no atmosphere, then we've learned that even planets in the so-called habitable zone aren't guaranteed to stay that way. The harsh radiation from their stars might erase their chances long before life ever has time to form. That means our definition of habitable needs more than just distance from a star. It needs stability, protection, and time. A planet can sit in the right spot and still be completely dead. But if TRAPPIST-1e turns out to have even a thin, nitrogen-rich atmosphere, then it flips that thinking on its head. It would mean planets around red dwarfs might not be doomed after all. They might lose their first atmospheres and rebuild new ones over billions of years. That makes them resilient, not fragile. It suggests that life might have more opportunities in the universe than we imagined. The discovery wouldn't just change how we think about this one planet, it would change how we think about all rocky worlds orbiting small stars. This observation also matters because it gives scientists a real-world case to test their models against. They've built thousands of simulations over the years, trying to predict what planets like this should look like. Webb's data gives them something concrete to compare those simulations to. Even small details, the depth of a light curve, the shape of a spectrum, the missing hydrogen lines, tell them which ideas hold up and which don't. It's how science moves forward. One uncertain result that forces 100 new questions. Another important part of this discovery is what it shows about Webb's power and limitations. Webb was built to see the faintest galaxies and the earliest light in the universe. Yet it's sensitive enough to study the air, or lack of it, around a planet orbiting a tiny star. That's not just an engineering achievement. It's a sign of how far exoplanet research has come. 20 years ago, we could barely detect these planets. Now we're analyzing their atmospheres, even if just barely. The difference is enormous. At the same time, the challenges Webb faced are lessons for the future. The problem of stellar contamination, the star's own light interfering with the planet's signal, is one of the biggest obstacles in exoplanet science. It's like trying to study a firefly sitting in front of a floodlight. But learning to work through that is part of the process. Every observation teaches scientists how to separate what belongs to the planet from what belongs to the star. Over time, those corrections get better, and so does our view. This discovery also matters because of what it represents. Not just data, but patience. Studying planets like TRAPPIST-1e isn't about one big aha moment. It's about building understanding, layer by layer. Each observation refines the next. Each ambiguity narrows the search. Even the possibility that the planet might be airless tells us something crucial about how life could form elsewhere. It reminds us that habitability isn't common, it's earned. And maybe that's what makes this finding exciting. It's not proof of life, but it's proof that we're finally capable of looking for it in the right way. Webb has shown that we can detect the difference between a living world and a dead one. We just need more time and more data. The fact that we're even arguing about the presence of nitrogen, haze, and heat retention on a world 40 light-years away shows how far we've come. What once felt like distant theory is now visible data. And with recent hints of life-link formations on Mars, it underscores a growing sense that extraterrestrial life may prove inevitable, if not imminent. The truth is, this might be the most important kind of discovery, one that doesn't give a simple answer. Webb's study of TRAPPIST-1e didn't find life, and it didn't confirm an atmosphere, but it showed us how close we are to being able to do both. For the first time, we're studying a planet almost identical to Earth in size and temperature, with enough precision to notice faint chemical hints in its light. That used to sound impossible. Now it's just data waiting to be refined. This moment marks a shift in astronomy. Until now, we've mostly been detecting planets, counting them, measuring their sizes, guessing what they're made of. Webb is changing that by turning distant dots into real places with measurable traits. It's teaching us how to move from discovery to understanding. TRAPPIST-1e is the first world of its kind where that transition is happening right now. It's no longer just a name on a list. It's a world we're starting to know. The result also says something about how science actually works. The absence of certainty doesn't mean failure. It means we've reached a boundary. Every time technology pushes that boundary, it shows us the scale of what's next. The same way early telescopes once blurred the moons of Jupiter before revealing them clearly, Webb's first looks at TRAPPIST-1e are the beginning of a sharper era. These faint, noisy spectra will eventually become detailed fingerprints of alien skies. It's just the start of that process. If the planet turns out to be bare, that's still powerful information. It tells us how fragile Earth-like conditions really are. It reminds us that distance from a star isn't enough. The story of habitability depends on time, radiation, and survival. But if the thin, nitrogen-based atmosphere is real, then this world has endured. That possibility carries a quiet message. Maybe planets like ours are tougher than we thought. Maybe they find a way to hold on. And beyond the science, there's a deeper significance. Every spectrum, every light curve, every pixel of this data came from a world 40 light years away. Webb isn't just seeing planets, it's seeing history, chemistry, and the building blocks of possibility. For the first time, we're not just imagining another Earth, we're starting to analyze it. That's not fiction anymore. It's reality measured in wavelengths.